So you have seen the bug here. When L and R is going to be very high values, the plus is causing the trouble, which is leading to negative index. Why is it? Let's take an example here. Let me write the most subtle bug here. In binary search is m equal to L plus R by 2 is causing trouble. Now, so why is it? In Java, integer takes 4 bytes now here. So integer normally takes 4 bytes. In other languages, slightly can vary here, but essence is same. Now, so when you have 4 bytes, how is the arithmetic actually happening up inside a computer machine? If you see it up, so when 4 bytes are available, idle 32 bits here. So we have 32 bits totally given for integer, first byte, second byte, third and fourth byte. The range of numbers possible, I told you in a human arithmetic, there is infinite. So there is no limit for numbers now. One after the other keeps coming up. But in computer, since we fix size anyway, there should be some limit after which it has to go back to the existing numbers on. What is the limit? We are trying to understand via a clock cycle. Here, 8 bits here, 8 bits now. So start from all zeros here, all zeros here, all zeros till the maximum number. Since integer takes both positive and negative numbers, mostly we dedicate the first bit or most significant bit for sign. The more details of computer representation, other video have seen it up, but I am utilizing the foundational storage representation to understand this bug. This is traditionally we call it a sign bit anyway. 0 means we give it for positive, 1 means negative. So once you taken off, that means maximum positive number, we start from 0. So 0, all is ones now here. That means 0, 1, 2, 3, like this, our clock cycle will end up at 2 power 31 minus 1. So if all these guys are ones here, the maximum positive number you are getting here. But after adding 1 to that, means ideally, so 0 and so on, all ones. Then so this is how we are going up, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, now 0 followed by all ones now. This is how when you plus 1, you keep doing it up, the arithmetic actually progresses here. So when you see this highest positive number, 0 is a positive, all these guys are giving up 2 power 31 minus 1. How did we arrive it? You take, let's say, 4 bits, you really get 15. If you have 31 bits now, the max number is 2 power 31 minus 1 because you are starting from 0. That's how we know 2 power 31 minus 1. When I add a plus 1 to this, then what do you get here? 1 followed by all zeros here. Since 1 is coming at the most significant digit position, this is negative number minus of 2 power. And in computer, again you refer to that video of computer representation of integers. This is a negative number. Negative numbers use 2's complement representation. We are not going to detail of that, but this is nothing but minus 2 power 31 we are getting out here. Now when you add 1 here, the next number, so the final number we are going to get is minus 1. Minus 1 is 1 followed by all ones. This is minus 1. When add a 1 to this, so we get all zeros, one more extra bit will become 1. Since 32 bit we cannot store, we are coming back to 0 here. So from here we are getting back to the cycle here. That means, so here we call this as cyclical arithmetic here. So in any computer machine, since size is fixed for specific type, the range of numbers are also limited here. Since we want both positive and negative integers here, we start from positive 0, go to maximum 2 power 31 minus 1, the negative number starts here, then again comes back to minus 1, after that 0, this keeps on happening here. It never complains when I add what they call after 2 power 31 minus 1 some numbers. Now it keeps going to the negative indexes and everything. So this is the foundation on which integer arithmetic happens any language. This is actually happens at a hardware level here. Now, so how is this related to our bug innovation? Let's look at L plus R by 2, how this is causing up an issue. To understand it up, since 32 bits are very big, let me take a very small size now to get a feel of how L plus R by 2 is causing an issue. What if I take up 4 bits now here? Just to understand the foundation here. 4 bits, so my clock cycle look like in this fashion here. So positive 0, 0, 0, 0, 0. Now 0, 1, 1, 1. Maximum is plus 7, plus then 1 here. In middle here, somewhere you get a 4. Then after plus 7, then we get 1, 0, 0, 0 here, which is minus 8. Then minus 7, minus 4, then minus 1. So if you have only 4 bits, assuming here a hypothetical example to get a clarity on the bug anyway here. So this is what an example I have taken. Now what if L is 4, R is going to be something here. So let me bring up L and R close to the maximum here. So if I really take 4, then that means if L equal to 4 and R equal to, let's say, in this case here, plus 8 here. Let's see what will happen. So it doesn't complain anyway. 12 is not possible, ideally speaking. In 4 bits, 12 cannot be stored. But if you take L plus R, 4 plus 8, what will happen here? First 4 we are reaching it out here. Then when next 4 we are going back to what now here? Minus 4. That means when you do L plus R, ideally speaking, by 2, it is really giving up 4 plus 8 movements now. It is going till minus 4. What you call divide by 2, it is doing up. It is giving up minus 2. If you try to access this as a mid index now, definitely it is index out of bounds exception. So in our case, later on we'll rate it up, but let's get onto clarity on this small example. That's where we got minus 2. So we don't want minus 2 here. So, and we know that when L and R mid by 2, 8 plus 4 by 12, 6 is a valid thing. 6 is somewhere here. Ideally we should get 6. It's a valid position, but because of our computer arithmetic here, once we are going beyond the maximum positive number, we are in the negative here. When I divide negative number by this 2, we always get negative index. This is source of the problem whenever this kind of overflow happens here in our integer addition operation. So what are the ways to fix it up? One of the ways to fix this problem here is, instead of going beyond this limit, reaching to negative divide by 2, let me write the fix innovation. First fix, we call it as fix 1. Now 4, I'll take it up, 4 plus. Now since my aim is to reach to 6 here, 6 is nothing but what they call, so ideally 4 plus 8 by 2 is 12 by 2, 6 we should get it up. This L plus R by 2, if I expand the expression, let me write L plus R by 2 first. L plus R by 2, we write into a slightly equivalent expression like this. L plus R minus L by 2. Are these two equivalent or not? If you try to see, here we have a L here, R minus L by 2, write R by 2 minus L by 2, L minus L by 2, we get L by 2 plus R by 2, which is exactly equivalent to the original guy. But what kind of benefit this, little different algebraic expression will help it out. If you see the meaning of this expression, now let me write L plus R minus L by 2 is our fix 1. This is what fix 1. So how is going to be helpful? L is in this case is 4. Now R minus L. R in this case is 8 anyway here somewhere. Now R we are initializing it up. R in this case, even if you take R, 8 cannot be possible. 7 maximum here. Take 7 also here. Not an issue. So here, so 4 plus 7 here. So 4 plus 7 is going to be almost 11. 11 means now. So or 7 after you add 4 more elements now. Minus 8, minus 7, minus 6, minus 5. Minus 5 by 2. Still we are getting a minus 2. Still the problem is there. Now when you take L equal to 4 here plus R minus L. R is 7 minus 4, which is 7 minus 4 by 2, which is nothing but 4 plus 7 minus 4 by 2 is 3 by 2. Integer division, you take it up, 4 plus 1, which is 5. Ideally, 7 plus 4 by 2 is 5. We want it up as a mid index now. We are getting exactly 5. But here we don't have overflow. The reason why we don't get overflow is because we are having 4 after taking subtraction. So that means 7 and 4, when I take subtraction, the gap we are getting up between this, how many numbers are there? That gap when I divide by 2 here, we are exactly within this range. When I move 4 to that position, without overflow, we are still in the positive range. That's why this slightly rearranged expression definitely going to solve this problem associated with L plus R by 2. This is one way to fix it. So this is there's other way to fix this as well here. Let me write the fix 2. Right, fix 2. So instead of what you call L plus R by 2 now here, if you look at the what you call the expression when you add a when you sum these two numbers here, so the alternative is going to be take L plus R as is anyway. Instead of using a slightly rearranged expression, I am using up bitwise operator. This operator technically we call it as logical right shift. Logical right shift. Refer to bitwise operator video to get more details about what this logical right shift will do. But in summary, this performs what you call division by powers of how much right side you are giving, 2 power of that. That's what it really performs here. L plus R divided by, since I gave 1, it is 2 power 1. So mathematically this expression is correct. So which is equivalent to L plus R by 2 only here. But how is it solving a problem here? If you look at it up, let's take L plus R here 4 and 7. When I take 11, so 11 is coming up. 11 in the 4 bits, how does it look like here? So since 11 is not possible to store here, we know that. So 4 plus 7 is giving up almost how much here? So if you look at in this case now, minus 5. So minus 5, that means, so minus 5, what do you call, inside this here, 1 is here, definitely, because negative number. So positive 5 is 1 0 1 0, take a 2's complement, which is nothing but, so till the rightmost 1, then 1, then 0, then 1. So whenever you want to store minus 5 here, we'll take a plus 5, take a 2's complement of that. Again, refer to the video of internal representation of integers here. So the minus 5 is stored here. Now after storing minus 5, what are you doing here? You got right shift by 1. This is not an arithmetic right shift which preserves sign bit. Since it's a logical right shift, it will not preserve sign bit here. It moves all the bits 1 to right. When you move all these bits one time to the right side, you get a 0. Then we move all these bits now, which is 1 0 1 here. Now what is the value you are getting up? This is nothing but, so 5 here. So let's see, minus 5 plus 5 here. 2's complement, we get a 1, again 1, 0, 1. Now when right shift it up, so 1 is coming up, 0 is going here, 1 is going out, we are getting 5. You can see here, 4 plus 7 by 2 here, 11 by 2, we exactly expect 5. Now again we are getting 5. Because logical right shift is doing a trick of taking out here this negative sign, hence we are able to get correct results here. That's why. So whenever you really see up this L plus R by 2 expressions, anywhere you write in the programming here, because these L and R of basic types which are limited by size, when you really take L and R to very extreme limits now, the summation directly, if you see, they take it to the negative index range here, then obviously division gives negative index, throws an exception. One way to fix them out here is rearrange L plus R by 2 by using slightly different expression, and which is giving exactly right answer, but without that index out of bounds. The other way to fix this problem is going to be use bitwise operator, where because of logical right shift, we now don't care about sign bit, which is incorrectly given. Movement is correct. Because of sign bit, we got a trouble. You just throw off the sign bit anyway here. By right shifting once here, then the sign bit goes off, then we are getting back to the positive 5 here. This is how we actually solve the problem of L plus R by 2. In our case, if you generalize here, what kind of size we are given in our test data? We are given up 2 billion. Somewhere I given 2 billion anyway here. L starts from 0, because I gave, the element is, I gave up the array, L is initially here, R is here, almost 2 billion array size. First time I am going to mid anyway. Mid is almost like a 1 billion. So since my X is still greater than that, now we are adding up what they call these two elements to go to mid of it. That means 2 billion plus 1 billion, almost I am doing such operation. So 1 billion is somewhere here, 2 billion is somewhere. When you add these numbers, we are already in the index, what they call negative index range. That's why we got that kind of index out of bounds exception. The same fix, what you are given for this small example here, still work for our integer size in our language here. That's what ideally one of the most subtle work here. Unless you really understand the L and R limitations here, it's difficult to reproduce it up. So this is what the background understanding and logic for how to fix this problem. Let's go back to the code and fix, apply these two solutions. Let's see we are able to come out, take off this bug or not. Let's move on to the coding. So you have seen what are the reasons now, what are the fixes possible. Let me see in practice here whether this fixes solves the problem or not. Let me try the fix one here, comment it out here. So first fix here, fix 1. So I take integer m is equivalent to L plus R minus L here divided by 2. So same test case, we have given 2 billion as vertical size of the array here. Now let me try whether you get index out of bounds or we get correct result in a vision. Now you can see there's an exception, and we know that since we're searching for last element, 2 billion minus 1th index is what you're actually getting it out. So this is how L plus R minus L by 2 is giving correct solution. The second fix, let me try here, comment, so fix 2. So integer m is equivalent to, so L plus R, end of this triple right shift by 1. So some languages may not have this operator here. Such cases here you can go for fix 1, but if a language supports triple right shift, which is logical right shift, you can use this solution as well. Even this is much faster. The reason here one is addition operation, one is subtraction operation, other is division is required. Here only addition, shifting, only 2 operations required. That's why this is definitely faster alternative than L plus R minus L by 2 here. So let's see whether we get correct result with the second fix or not. Again, same 2 billion elements are given it up. Now again we got correct result here without any so-called index out of bounds exception here. That's what the common solutions. I'm sure if you open your library here, wherever you see it up, this is what they are going to use it up. So the reason for such kind of tricks is because they found that this is a kind of bug they can able to reproduce it. So in this video, so that's what we want to talk about. What is the most common thing we need to care in the computer arithmetic is addition. When keep adding numbers, always you got to think twice. For what large values of n is the summation is going to work out, or is it going to take into the out of bounds and a. So that's what this video is all about.